Okay, so last time we were looking at a heuristic for the traveling salesman problem. So again, the traveling salesman problem is given a complete graph with edge weights like this in a matrix. We want to find a tour, and we are really targeting for a minimum weight tour. But again, this is a heuristic for an NP complete problem, so that means it's not guaranteed to give us the optimal solution. It could give you for some graph, it may not give you the optimal tour for another graph. So you always say it gives you what is called an approximate solution. And we also don't know what is the optimal tool because that is NP complete problem. So we don't have a deterministic algorithm that will give us, okay, for any complete graph with edge weights, this is the optimal tool. We don't have any such algorithm available so far. So what we saw last time is this heuristic. We're going to look at two heuristics. One of the first of the two heuristics is the nearest neighbor heuristic. We went through the process last time. Let me just quickly go through that. So it's quite easy. We start with some arbitrary vertex, start with the lower ID vertex to as a convention and go to its nearest neighbor. That's what the name itself means, nearest neighbor. So vertex 3 is the nearest neighbor. So vertex 3 is added to the 2. So now from 3, we'll try to go somewhere else. So again, vertex 1 is already listed in the 2, so we have to go to an unvisited neighbor. So of course, this is a complete graph, so every vertex is a neighbor of every other vertex. So we can go to the nearest neighbor distance is 5, so you break the tie by going to vertex 2. So vertex 2 is now added to the 2, and from vertex 2 we can go to anything like v4, v5, v6 because v1 and v3 already visited. So we go to vertex 6, that's the nearest neighbor. So add vertex 6 to the 2, and from 6 we can go to either 4 or 5. So we'll pick vertex 4, that's the nearest neighbor of distance 5. So go to vertex 4. Now after visit vertex 4, we have to visit vertex 5, there's no other go. So we don't have any control on these two edges that are v4, v5. So start from vertex 1, we go to v3, then v2, v6, v4. So until that point, we could kind of have some say on what edges we pick. Of course, as you see, to begin with, yes, we had complete control. We could pick the smallest weight edge that is possible, and then as we proceed, we start losing our control on really picking the minimum weight edges. We end up picking whatever is available as minimum, and then this edge v4 to v5 as well as this edge v5 to v1 could be really of any weight. We cannot say we don't want to pick them. We have to pick those two edges because that's the way, that's the nature of this heuristic, right? Nearest neighbor, but as we picked all the neighbors and formed the tour, for the last vertex to be included in this tour, we have to pick that vertex and use the associated edge. So that's the drawback of greedy strategy. So now, after we formed the tour, we found its weight to be say 30. That we could try to kind of improve the weight in the sense that we could try to reduce the weight of the tour and find a different tour. And for that, we saw a heuristic called a two-change heuristic. So the way the two-change heuristic will work is this. You want to remove two edges from this tour that you just found and add two new edges. And again, this is a greedy strategy driven. So in the greedy strategies, always you can kind of have a feeling by now that the initial choices that you make kind of drive you further. Okay, so in the two-change heuristic, the greedy strategy is, of course, we want to reduce the weight of this tour. So why can't we just remove the edge with the largest weight from this tour? Okay, so that's a greedy strategy. So we'll remove that edge with the largest weight, which is between v4 and v5. So this is the costliest edge that we removed. So because of this, now everything further we do is driven by that. Okay, so now we want to remove two edges because of this nature of two-edge heuristic. So we will have to remove one more edge. Now we could think, okay, the next costliest edge is this weight 6. Why can't we just remove it? But if you remove that, vertex 5 is going to get isolated. So we really cannot remove that edge, because if you isolate vertex 5 by removing this edge, we have removed two edges. We are done with removals. We have to add now two new edges. Whatever you try, you cannot add two edges and make the resulting sequence a tour. Okay, again, a tour means it has to have like a cycle where now every vertex has to have a degree of 2, has to have just two neighbors. So you cannot make a tour by isolating vertex 5, actually by isolating any vertex. So in that sense, you cannot even remove this edge v4, v6, that will isolate vertex 4. So that means once you remove the costliest edge, you cannot remove its what is called adjacent edges or edges next to it. So that means once you remove this edge of weight 9, you cannot remove v4, v6 or v5, v1. So that means among the remaining edges out there that are not adjacent to this v4, v5, only among those edges you have to remove an edge. So again, we will apply a greedy approach there. So among the remaining candidate edges that we could really remove the edge with the largest weight. So you have 3, 5 and 2 as the candidate edges, so we'll remove 5. So 5 is now gone, so we are left with now kind of two broken sequences, v1, v3, v5 and v4, v2, v6. You can call them as a component because these three vertices are reachable to each other, these three vertices are reachable to each other. So you have two components now. So now we have to connect these two components using two edges. So what two edges we will use? Now we don't have again much choice. We can connect either v3, v5 and v2, v4, but that's not really a valid choice, because if you connect v3 to v5 and v2 to v4, those are like two edges added, but they are not really connecting the two components, so they will be still in one component. They will be still in their own component. So we want to connect these two components and make them as one component. So the only way we can do that is connect v5 with v2 like this and v3 with v4. There is no other way we can connect these two components and make them as one component. Okay. So now you see we started with removing this costliest edge. So everything kind of got driven from there. We don't have much control on the other things we do. Like in this case also, we want to connect these two components. Do we have choice on what two edges we add to connect these two components? No, we don't have any choice on what two edges we add to connect the two components. We have to really pick these two edges between v5 and v2 and v3, v4. Now again, those edges are there because it's a complete graph, right? But what about the weights of those edges? There could be any weight. So in this case, in this given complete graph, these two edges are of weight 3 and 5. So we have to check, or were we lucky to be using these two edges, because we have to check whether we have really reduced the weight of the tour, right? So by putting these two edges together now to connect these two components, we have a tour now, because even though it doesn't look like this is a tour, it is a tour. We can go from say v1 to v3 to v4, then v6, v2, v5 and then v1. That's a tour. But have we reduced its weight? We have to check. So we started with some tour here. We removed two edges of weight 9 and then 5. So we removed edges adding up to 14 as a weight, 9 plus 5, and ended up adding two edges of weight 3 plus 5, 8. So removed 14 and added 8. So that's the saving. So that's why I show in the slide here. From 30, we do 30 minus 14, the thing that we removed, which is then 16. 30 minus 14 is 16, plus 8 that we added. So 16 plus 8 is 24. So from 30, we are able to reduce to 24 by choosing these two edges, and by the two change heuristic was effective here, was successful here basically, and reduced the tour weight. So now, is the two change heuristic going to always work? The answer is no. So that's what I want to illustrate now. As I said, once we use a greedy strategy of removing the costliest edge, we don't really have much control. So once we have the two components, we have to use those two edges available to connect the two components. So what if the weight of those two edges that we added, like in this case instead of 3, it is say 13 between V2 and V5, and let us say it is 5 as before. So 13 plus 5 is 18. So remember, we removed 9 and 5, so they add up to 14. So we remove some two edges of weight adding up to 14 and add two edges with weight adding up to 18, more than what we removed. So that means we are going to say 30 minus 14 plus 18, which is 34. So we are not really improving, which means we are not really reducing the weight of a tour. We are kind of actually increasing the tour weight further. So that means the two change heuristic is not successful. So in that case, we will retain with the original tour, will not switch to a new tour. Okay. So why I am telling this? So for exam, for each of you, so you could have checked by now, assigned the final exam. For each of you, I have given a graph for the 4 questions, I think. So on this question involving traveling salesman problem and finding the tour using this heuristic, or both this one and the following heuristic, you have to try applying the two change heuristic. So after you get the original tour by applying the nearest neighbor heuristic, you have to try to apply the two change heuristic. Now depending on the complete graph edge weights assigned to you, it may be that you could reduce the weight of the tour further like this, or it may not be possible to reduce the weight of the tour if you are ending up with something like this. So it could be one of these two cases. So you have to look out for that, work out the numbers, and then say as part of your answer, show, of course you have to show the two change heuristic done like this, even in this case, and then say because the weights add up to more than what the original tour weight is, I'm not going to use the two change heuristic, I'm just going to stay with the original tour. If the weights add up to something in such a way that you could reduce the tour weight, you have to also show all those things and say, okay, the new tour is this, and the corresponding tour weight is whatever the tour weight is. Okay, so that should be the way you should answer such question. Any question on this? You can type or ask me over the microphone. Let me save this and I'll come back.